Okay, this is week 5 of the summer session. All of you are kind of used to the process by now. Okay, so this is test number 4 on Thursday. Which is going to be a lot of matrix related calculations and operations. Okay, which I mean, if you don't make mistakes, it should be a pretty easy test. If you make small mistakes, it can be pretty annoying and stressful. So we are kind of doing these two together because they cover the same concept. Okay, there's no need to really split it into two sections. So we talked about what a raw echelon form looks like, an ordinary raw echelon form. Okay. And if a matrix is not in echelon form, you could do any one or more of these operations to make it happen. Okay. So in particular, all these operations are related to the row or the rows of a matrix. It's never with the columns. Okay, you could take a row, multiply that row with a number, add it to another row. This is probably the most popular operation because it kind of helps you manipulate numbers. Okay. You could also multiply or divide a row with a non-zero scalar, or you could even swap two rows, and you could do it any number of times as you want. Again, all these things are done with some purpose in your mind. Okay, you're trying to get some kind of structure for the matrix. So this is not some kind of a random process that you just keep doing without any particular aim. Okay. So we'll start with a couple of examples with this and then show you how to make use of this in solving equations. Okay. So that's where we were. Before I start, do you have any questions about anything? Can people hear me online or? All right, good. Okay, so while people are slowly getting in, I'm just going to leave it here for a few minutes. Okay. Jump into an example right away. I have to copy these examples very carefully because if a number or a sign gets a little off, this could be a nightmare. So, and the same applies to you. Okay, please copy these problems carefully. So example 1. Write the following matrix in the raw echelon form. Just going to use the abbreviation REF. Okay. Again, echelon stands for this staircase pattern that I've shown here. And there is no particular niceness that you expect with the staircase. It could be kind of really stretched out or nicely symmetric. Okay, that depends on the matrix. So here is the first example. 1, -3, 7, 2. So I'm reading it row wise. Okay, 0, 1, -10, 4. And -3. Sorry, I think I wrote the answer. That was not my intention. The second row is I need to read it from the question. 2, -5, 4, 8. Sorry about that. And the last row is -3, 1, 0, 9. So what I wrote earlier was what you would get after the first step. And this is why I don't like looking at things in writing, because I never look at the right things. Okay, so the question is, write this in the raw echelon form. Obviously, this is not. Okay, this is full of all kinds of things. The good thing is that we have one here. Okay, that's a good start. So this is good, because the first non-zero entry of any row must be a 1. Okay, so if it is not a 1, you have to make it a 1. But in this case, the 1 is waiting for you. We need to make this a 0 here. Okay, and this is where you need to have a definite plan going into the problem. You need to know what exactly we are trying to achieve and not just do some random things. Okay, so we need a 0 so that we have the numbers below each leading 1, they all must be 0. Okay, so we need a 0 here and also here, but let's do it one at a time. Okay. So let's focus on this 2. And to get a 0 here, we are going to take twice the first row and subtract this row. Okay. So I'm going to write row 2 minus 2 times row 1. Okay. Now that's a lot of writing. You don't want to keep writing this row 2 minus 2 times row 1 each time. So the usual way we write this for problems like this is write R2 minus 2R1. That should tell you what we are trying to achieve here. And the same should be done for when you're writing this on a test or something, please make sure that you clearly show what operation you're doing so that I can know what you're doing. You can also correct yourself. Okay. So R2 minus 2R1, and that will help us get a 0 there. Okay. So the first row should not be changed. 1, -3, 7, 2. R2 minus 2R1 would be 0. This would be -5 minus 2 times -3. And that's going to be -5 plus 6, which is 1. That's a bonus 1, okay, because we need the first non-zero element of a row to be 1. 4 minus 2 times 7, that will be -10. And 8 minus 2 times 2, that is 4. And that is what I wrote earlier, 0, 1, -10, 4. And since it's the first example, I'm just going to do one at a time. So I'm not going to touch the third row. Okay. So with more practice, you could do multiple operations. Okay, so the one thing that you cannot do is to take the second row and just subtract 2. Okay, you shouldn't do that. You should always use another row as a pivot to make your operations possible. Okay, so please. Usually 1 in 100 students try this kind of stunt. Okay, so please do not do or try just R2 minus 2. Okay. I know 2 minus 2 is 0, but you cannot do that in a matrix. Okay, you have to use another row to get that 0 happen. Okay. Maybe this is obvious, but just in case you were thinking, oh, we don't have to do this, just subtract 2 from the second row. That's not nice, or that's not correct. Okay. All right, here is a silly question. How do you get a 0 here? I know it's a embarrassing question, but how do you get a 0 there? People online can also pitch in. Yeah, so add, how did you say that? Not this kind of add 3, no. Okay. So which row are we going to use here? R3 plus 3R1, yeah. Is that what we're trying to say? Okay. So when you said add 3, it seemed like you're just adding the number 3 there. So add R3 plus 3R1. Okay. So it'll be 1, -3, 7, 2. Every time you have this burden of copying the matrix correctly into a new one. Okay, so 0, 1, -10, 4. R3 plus 3R1 would be 0. 1 minus 9, which is -8. 0 plus 21, that's 21. And 9 plus 6, which is 15. Okay, so we have this, and the numbers below the first leading one are both zeros. Okay, that's good. You're making some progress here. So this is progress, this is progress. Okay. Our next target should be this thing here. Okay, we need a 0 here. How do you make this happen? Or look at the ones above it, to try to keep things easy. Yeah.
R3 minus 3 R1.
You don't want to lose the 0. Okay.
Oh.
Keep it. I mean, whatever we achieved before should stay there. And you're trying to get a 0 out of this one. The hint is in this 1. How do you do it? Yeah. Why would you do a 9? We need a 0 there. R3 plus, what is the number? 8 R2, right? Okay. If you could do 9 R2, but let you be a 1 here, and then you have to do another subtraction to get a 0. I mean, you could do that, but that's extra work. Okay. None of these steps are wrong. You should just do it efficiently so that you don't just keep on doing this forever. 1, -3, 7, 2, 0, 1, -10, 4, 0, 0. Okay, that is what we're trying to do. And now we have 21 minus 10 times 8, which is 80. That's a -59. And you have 15 plus 32, which is 47. So we have 1 there, 0, 0, 0. Okay. Make sure that once you get some of these, don't lose it. Keep it because they're precious. Almost there. Okay. Now we need a 1 here because the first non-zero leading entry of a row should be a 1. Okay. How do you get a 1 out of this number? Without over complicating it. What is the easiest way to get a 1? Yep. So divide by -59. Okay. So R3 divided by -59. Again, you cannot add 60 to it. Okay, so R3 of -59 is 1, -3, 7, 2, 0, 1, -10, 4, 0, 0, 1, -47 over 59. Okay. That is not your fault. That is how the matrix was constructed. So this number is here. That's fine. Okay. Our main task is to get these ones in this staircase pattern. Okay, that is the row echelon form. Everything under the leading ones should be a 0. Okay. Right now, we don't care about what these numbers are. Okay, that is an REF. So that is the final answer. Should keep in mind that the REF of a matrix is not unique. Okay, you could probably do more simplifications there and get a different REF. So REF answers are not going to be the same for, but these things should be the same. Okay. The positions of this 1 and the zeros below it, those things should be the same. Some of you might do more simplifications here, okay, which are not required, and get a different REF. That's fine. All right, so that's going to be our main theme for today's and tomorrow's lecture. Okay, these operations to get ones and zeros without violating any of the 3 processes that I've listed there. Any questions about this? So again, I did not go on some kind of a random process. Okay, I have a definite idea in mind as to what to achieve here. Started with trying to get a 0 here, here, and then every position which is below a leading 1 should be a 0. Okay. All right, can you try one yourself? It can be a bit frustrating at first. Okay, so that's part of the game if you've never done this. So here is the next one. Let me erase all this. Example 2. Write the row echelon form for the following matrix: 2, 1, -1, 1, 0, 2, 0, 1, 3, and 1, 2, 4. So it's a 4 by 3 matrix. Okay. So just take your time and see what you can do. Again, all these 3 operations are at your disposal, so make use of whichever you think would be appropriate. Okay. don't underestimate the power of this one. Remember, you've got a million different possible ways of doing this problem. The answer should be pretty much the same, but the way you do it, it's up to you. My first question is, should I divide the first row by 2? You could, but the answer is I don't have to. So yes, but not my first choice. Not my first choice because that will give me some fractions here and here. If all of them were multiples of 2, maybe that's a good idea, but since 1 and -1 won't give me clean numbers. Okay, so not my first choice. But if you want to divide the first row by 2, that's also possible. Okay. Sorry, I turned off the microphone when I was waiting for you to do it. Sorry. All right. So what will be your suggestion now? If you don't want to divide the first row by 2, what else can you do? Yeah, you could swap row 2 and row 1 or row 4 and row 1. Okay, all possible cases. So R2 swap R1. Okay. Swap with those double arrows just to show what exactly you're trying to do here. So it's going to be, when you're swapping, you have to swap everything, okay, not just things that you like. So 1, 0, 2 should all move up there. Okay. 2, 1, -1, 0, 1, 3, and 1, 2, 4. Because it's always, it's a good feeling to have a 1 up here. And then, first of all, that's a requirement of REF, and also it's easy to manipulate your calculations based on that. Okay. Now you can do R2 minus 2 R1. And you can also do another operation here. You can also do R4 minus R1. They're not going to conflict with each other. Okay. Or you could do it separately, but you could do that. But whatever is, if you want to swap row 2 and row 3 now or later, there's no way to know it beforehand which one is better. So, okay. The first swap was pretty obvious, probably because of the position of that 1 and 2. So let's do this. But if you try it the other way, you don't have to correct it or anything. Okay. R2 minus 2 R1 is 0, 1, -5. And I'm not changing R3, so 0, 1, 3, and R4 minus R1 is 0, 2, 2. So I did 2 operations there in that one matrix there. Okay. And if you spot any mistakes, let me know. Going to divide the last row by, okay, let's start with this one. R3 minus R2, okay, because you have one here, one here. We want to get this guy out of there. Okay. So R3 minus R2 to kill that one. And also let's do 1/2 R4. So it's 1, 0, 2, 0, 1, -5. R3 minus R2 will give you 0, 0. It's about to write -2, but it's not. R3 minus R2 is 8. And 1/2 R4 is 0, 1, 1. All right. We need to get rid of this one. Okay. Some of you might be thinking you could have just done R4 minus 2 R2. In hindsight, that's what I should have done. But R4 minus R2 will give you 1, 0, 2, 0, 1, -5. You can also divide the third row by 8. Okay. You don't have to wait for another step to do that. 1/8 R3 and R4 minus R2 is 0, 0, 6. We'll do a 1/6 R4, 1, 0, 2, 0, 1, -5, 0, 0, 1, 0, 0, 1. Okay. So these ones are all nicely arranged, but this one shouldn't be here, okay, because below each leading one should be a 0, and that could be eliminated by doing R4 minus R3. One, 0, 2, 0, 1, -5, 0, 0, 1, 0, 0, 0. I have a feeling that in the past I've done this in fewer steps. I don't remember, but and maybe some of you would have probably done this by doing this as R4 minus 2 R2. Okay, so multiple operations are possible. Can we swap R2 and R3? You could swap and try different things. At the end of it, it should get that pattern. So where and how you do it, it's your choice. Okay. So if you feel like you could swap this and this, that's probably worth a try in some problems. Okay, but at the end of it, this should come in this pattern here. This shouldn't be offset to another way. Okay, so this is what we are trying to achieve. That's the final answer. So it's possible that no two of us are trying the same operations at one time. Okay, that's fine. Any questions about what or how these things are happening? No, there is nothing conceptual about it. It's more about not making mistakes, which so far I've been able to avoid. Next definition. You know what a raw echelon form looks like. We can make a few more adjustments to it and make it more unique. So a reduced raw echelon form. Abbreviated as RRAF. Well, first of all, it's an REF, okay, of a matrix is an REF, which means all those things are still true, with the following condition, with zeros above each leading one. So far, we did not really bother about what was above each of those leading ones. We just focused on what is below it. So for example, we did not really care about if this is a -3 or if that is a 7 or -10. Okay, that is none of our concern. And same for that answer there. Okay, that the third column had a -5 and 2 above it, right? So now we are making it even more stricter. Instead of having random numbers above the leading ones, we're going to insist on zeros. Okay, this means zeros above each leading one. Now you're going to make it more unique. Okay, that REF representation up there, it's not unique. This is unique. The RREF of a matrix is unique. So there is only one RREF for a matrix. The REF could keep changing depending on where you stop and how you simplify things. Okay. And that's why if you look at your REF answer and compare with the back of the textbook, you might see some small changes. RREF is the same. Okay. REF of a matrix is not unique. Which means that once you hit this particular format, okay, where you have zeros below and above each one, there is nowhere else to go. Okay, you're kind of stuck there, and that should be the end of it. So let's do a couple of examples. Okay, let's choose the ones that we've already done. Let's try to do this example. Okay, so example 3. Write example 1 in RREF. So that we don't have to start something from scratch. Okay. So this answer is already here. My objective now is to make these things, the ones that I'm putting within this rectangular boxes, those should be equal to 0. So let me write that answer here so that it's easy for me to see this. 1, -3, 7, 2, 0, 1, -10, 4, and 0, 0, 1, and this ugly number -47/59, which I hope we won't have to deal with a lot. Okay. So we need to have 0 here, 0 here, and 0 here. The only unpleasant part about this set of calculation would be to deal with this nasty stuff. All right, who's going to tell me how to get the 0 here? Let's start with one at a time. Can somebody online tell me how to get to 0 in that first row, second column? R1 plus 3 R2. Okay, good, because there's a 1 waiting here. Okay, so R1 plus 3 R2, that's going to be, you should not lose anything else. Okay, this 1 should be here, the 0 should be here. Nothing else is changing. The only thing that is changing at this point, this is 3 or this -3. So it's going to be 1, 0, R1 plus 3 R2 would be -23. 11, 0, 1, -10, 4, and 0, 0, 1, -47/59. So that one escaped the wrath of that fraction. So we have made some progress there. Now we need to make these two equal to 0. Let's start with one at a time. Okay, let's not do too many things here. How do we make this a 0? Anyone sitting here can? All right, so R1 plus 23 R3, and that gives you 1 0 0 and some number. Okay, just going to put like this down. Okay. 0 1 -10. When you get some free time, just calculate what the number is. Okay. 11 plus 23 times this bleep here. So 0 1 -10 4 and 0 0 1 -47 over 59. I try my best to avoid fractions in problems. Okay, so this was an unexpected visitor here.
Let me put
Which one?
the 11.
Oh, is it? That's a clean number?
No, I'm saying it's not supposed to be 11. It's supposed to
Oh, this one? 2 plus 12, isn't it? 2 plus 12 is not 11? No, it's 14. Okay. Either way, it's a sad face here. Thank you. All right, what is remaining? This creature here. Okay, so how do you convert that to 0? All right. So it's 1 0 0. Sad face 0 1 0. And 0 0 1 -47 over 59. I know some of you are dying to do the decimal part of it, and thank you. So when you do this on a test or something, please show these steps, okay, so that I know what you're trying to do. I know it's a bit annoying, but if you make a mistake later, it's easy for you as well to go and retrace it. So that is the RREF for the matrix that I gave in example 1. The good thing is that you have a lot more ones and zeros. Okay. So when you're solving a system of equations using this matrix, for example, this has got a lot more potential in saving time. Okay. The only problem is you kind of wasted time here. So it's always a trade-off. So it's never a perfect answer as to whether REF is better or RREF is better. Sometimes you do some work up front, sometimes you do work later. Okay. Can you do the second one in RREF? That is a much easier one. So example 2, take that matrix in the top right corner, and probably needs only 2 changes, I think, and write RREF for that one. Okay, online people, can somebody tell me what you would do to get a 0 here? This position with the 2 inside the flower. R1 minus 2 R3, good. So R1 minus 2 R3 will give you 1 0, oops, 1 0 0, 0 1 negative 5. Nothing else should change. Okay, you're only changing the first row, and that in particular just that one number 0 0 0. Okay, so just one more bad thing remaining, that negative 5. So I'll ask somebody here, how do you get a 0 here? R2 plus 5 R3. Okay. So this is a much more neater matrix than the previous one. You don't get a better matrix than this with ones and zeros. Okay. There's no other number anywhere. So when you're solving a system of equations, it just gives you the solution, chop, chop, chop. Okay. Okay, so that is how you write any matrix in its REF or RREF as required. Okay. And a choice between REF and RREF, it's usually something that you have to decide while doing the problem. And I'll tell you what should be the basis for that decision-making process, okay, when we start doing the next part. But before I do that, do you have any questions about REF, RREF, raw operations? Why R1 minus 2? Yeah, we need ones above, sorry, we need zeros above each leading one. So this is a leading one, that's a leading one. Okay. So anything that is above it should be zeros according to RREF. So row 3 or row 1 column 3 and row 2 column 3 should be both zeros. Okay. Good. Any other questions? All of you understand the modus operandi here? Okay. Let's start trying to do what exactly this is meant for. Remember, we are doing 4.2 and 4.3 together. Okay, so systems of linear equations. So in particular, I'm going to make it as general as possible. We have m equations and n variables. Now, since we have so many equations and variables, it's more sensible to use subscripts instead of just writing letters. Okay. So the first equation would be a11x1 plus a12x2 plus a13x3 dot 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 plus a1n xn equal to b1. That's the first equation. So a11, a12, a13, those are all coefficients which we know. x1, x2, x3, those are the variables. b1 is the number on the right hand side. Similarly, a21x1 plus a22x2 plus a2n xn equal to b2. Keep on writing equations one after the other. The mth equation, okay, m as in mango, mth equation would be am1x1 plus am2x2. My battery died. All right, back in business. am1 x1 plus am2 x2 plus dot 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 plus amn xn equal to bm, okay, because that is the mth equation. So you can think about it probably as 35 equations and 43 variables. Okay, there is no way you're going to sit down and manipulate equations written in that form. It's pretty unfriendly, and that is where the matrix representation is useful, okay, which is equivalent to the following. Matrix A11, A12, dot dot dot, A1n, A21, A22, A2n, AM1, AM2. So m equations and n variables will give you an m by n matrix there. Okay, this is the m by n coefficient matrix. Let's call it A. Okay, that's a standard way of denoting this coefficient matrices. So m rows, n columns, okay, that is filled with all the coefficients of the equation, times the vector of unknowns, which is x1, x2, dot dot xn. This is a n by 1 vector, also a matrix, okay, of unknowns x1, x2, x3, x4, etc. And to just remind you that these are now compatible for multiplication. Okay, the number of columns here and the number of rows here are the same, so the product should be a m by 1 vector, okay, and that's equal to b1, b2, bm. Okay, that is m rows, not n rows. Okay. It write it as a vector because it has just got one column, okay, and this is another vector. So this is a vector in the n-dimensional space. This is a vector in the m-dimensional space, okay, because there are so many of them. So this is the coefficient matrix. That is the vector of unknowns. That's the vector of some numbers. Okay. So you'll see that most textbooks write a system of linear equations in this format: ax equal to b. When you write like this, it has a lot of information kind of embedded in there, because A is a m by n matrix. This is a n by 1 vector. That's a m by 1 vector. So when people say solve the system Ax equal to b, okay, that doesn't mean just one number here. That could be a big matrix. All right. In particular, if b is not equal to 0, which means the right-hand side has at least one non-zero element. So if b is not equal to 0 vector, then the system is non-homogeneous. The same terminology we use in differential equations. And if b is equal to 0, which means all the right-hand side terms are equal to 0. Okay. This means that b1, b2, all of them are equal to 0. The system is homogeneous. Those names should not be surprising, because we had the same concept even in differential equations, right-hand side being equal to 0 or not. Okay. Okay, so our objective is to solve for this vector x1, x2, x3, xn. Okay. We know everything else. We know the matrix A, we know the vector B. Okay. Our sole objective here is to solve for x. which means all its components, x1, x2, x3, everything that is in this. Okay. So some textbooks write it like this to save space. Okay, that's the same as writing it as a vertical column, x1, x2, x3, xn. Those are the same notations. And when you say how many solutions are there, it actually means this one vector. Okay, you don't really count this as each solution. So how many solutions are there means how many vectors x would satisfy that system. That is what it means in linear algebra. So how do we solve this? Well, the most well-known algorithm is probably the oldest one possible. Okay, it's called the Gaussian elimination. This is what is still used in industry with some modifications to speed things up, but this has been in use for I don't know how long. Okay, and it's pretty efficient. So Gaussian elimination is, as the title says, it eliminates variables and keeps it one at a time. Okay. So the idea here is to eliminate n-1 variables and solve for just one variable. Okay. And then back substitute. You can think about it for a 2x2 system. You have two equations, two variables, so x and y, eliminate y, find x, plug it into the other one, find y. So same idea here. If you have 1,000 variables, you don't want to sit down and do it by hand. Okay. So the idea is still the same, eliminate all but one and keep one and back substitute. So the steps are as follows. Write the augmented matrix. The word augment means to join. Okay. So the augmented matrix with the vector B augmented to A. The purpose of doing this is to make sure that you do the same changes on both sides of the equation. Okay, so if you're multiplying an equation by 2, you don't just multiply one side of the equation. So this augmented matrix makes sure that all the calculations are done in a consistent way. So it looks like this. Now this was conveniently placed here for me, but you might have to write it again. So you have this m by n matrix and you attach the right hand side here. That is what an augmented matrix looks like. Now it's easy to get confused about which matrix is the one that you got in the question and which one is augmented. Okay, so just for sanity reasons, you put a vertical line to separate it so that you know the last column is the augmented column. Okay. I would strongly recommend that you put the separator line just so that you won't go crazy looking at it. But it's not a rule. If you do it without it, I don't take off points or anything. Okay, just for your convenience. So usually we denote it by A augment B. So it's an extra column now. It's a m by n plus 1 matrix. Okay. Step 2, reduce the augmented matrix A augment B. B is a vector. Okay. Into its RAF. Those of you who are fans of RREF could do that as well. Okay, I have no choice in between. So or RREF. What is the difference? This has got less work up front, more work later. This has got more work up front, less work later. Either way, you have to do some work. Okay, so it's a question of when to do that work. So this has got fewer steps earlier, but a little bit more work later. Okay. This has got more work earlier, but fewer steps later. Because you need to get those extra zeros above the leading ones. So that will give you some extra work to do there, but that will simplify your life later, okay, compared to REF. I would be mostly sticking with REF because that is what I prefer to do, but it's your choice. All right, so reduce the augmented matrix into its REF or RREF. Now you have a nice structure because all these ones and zeros. Okay, you start with the bottommost row. So step 3. Start with the last row. Solve for xn. And that is why this echelon structure is useful, because you've got a lot of zeros before that. Xn is the only variable remaining there. Okay. And then step 4, back substitute. Into the rows above it. And at each step, you're trying to solve for one variable at a time. Okay. And solve for xn minus 1, xn minus 2, all the way to x1. So x1 is typically the last variable you solve because you're going backwards. Okay. So there's a lot of research going on to speed this up by making the matrix as filled with zeros as possible. Okay, that's what computational people do, because solving these equations is part of a lot of research work. So, but the ultimate starting point is always the Gaussian elimination. From there, you could do a lot of things. So I'm going to do 3 examples today, one with something conceptual to teach you. Okay. So all these row operations are still there, but you need to kind of understand what exactly happens at the end of the problem. Okay. That's where you have to pay attention. Okay. Any questions on the Gaussian elimination process? Maybe you have seen this in other classes, or you have done this unknowingly without knowing it's a Gaussian elimination process. Okay. And you will get a chance to do one of these on this week's test. So it's nothing remarkable or wow about it, but you need to practice. Okay. All righty, here's the first example. I'm going from the most boring to the more interesting to the most interesting. Okay, that's the order in which I'm going to do this. So example 1, this is going to be slightly boring. x1 plus 5x2 plus 2x3 equal to 1, negative x1 minus 4x2 plus x3 equal to 6, and x1 plus 3x2 minus 3x3 equal to negative 9. Okay, so the question is to solve this using Gaussian elimination. You might think, oh, why don't I just plug in some equations into the other? You're effectively doing Gaussian elimination there, but the matrices kind of will help you keep track of things easier. So first example, so I'm going to write all the details. So the matrix equivalent of this would be 1, 5. Those are the coefficients. Okay, 1, 5, 2, augment 1, negative 1, negative 4, 1, 6. Too much gap there. Negative 1, negative 4. Okay, so just to show you that it's very easy to make small mistakes which can lead you into all kinds of time wasting issues. Okay, made a small mistake there purposefully. Can you tell me which one? Yep. So this should be a -3. Okay. So if you try +3, you might end up with some really nightmarish calculations later. Just take that extra few seconds to copy everything, right? I hope everything else is correct. Okay, this is a pretty easy matrix. So this is the augmented matrix, A augment B. Okay. This one is already there. You don't have to do anything extra. Let's do your typical REF. So R2 plus R1 and R3 minus R1. So the first row is unchanged, 1, 5, 2, 1. R2 plus R1 would be 0, 1, 3, 7. Not asking you what they are because you're just adding numbers. And R3 minus R1 is 0, -2, -5, and -10. Good, so made some progress there. So we got a 1 there, 0 here, 0 here, and a 1 there. Okay. So it looks like all that remains for an REF is to, at least for now, make that a 0. Okay, so that's going to be R3 plus 2R2, 1, 5, 2, 1, 0, 1, 3, 7, and 0, 0. R3 plus 2R2. Am I getting a 1? Haha, good. And this would be 14. No, -10 plus 14, 4. So if you are just an REF fan, you're done. Okay. So you got 1 here, 1 here, 1 here. They're all nicely stacked up like this. Okay. So that is the REF of A. So now you need to understand that each of these rows here are standing for equations. Okay. So the third row, row 3, at this point is giving you 0x1 plus 0x2 plus 1x3 equal to 4. Row 2, and this is the small inconvenience with REF compared to RREF. Okay, the RREF would have probably kept a 0 here. That way, it would have said R2 equal to something. Okay, but now you have to do this extra term, which is x2 plus 3x3, 0x1 plus x2 plus 3x3 equal to 7. Not the worst thing when you compare REF versus RREF. Okay. So x2 is -5. And the first row, which we did not do anything with, it stayed the same throughout this process. So just go back there and plug in everything. So row 1 gives you x1 plus 5x2 plus 2x3 equal to 1. And we know x2 and x3, that's the whole process of Gaussian elimination. Okay, so we have x1 minus 25 plus 8 equal to 1. So what is x1? -26 minus 8, 18. So x1 is 18, x2 is -5, x3 equal to 4. Okay, and I want all of you to develop the practice of writing the answer in an efficient way. The final answer is vector x equal to x1, x2, x3. This is something we're going to do throughout this throughout the linear algebra part of this course. So please arrange your answer in a vector form, okay, equal to 18, -5, and 4. So that is not complicated, or there is no drama going on here. Okay, so it is a system of 3 equations, 3 variables, and if somebody is asking you how many solutions did you get for this problem, what is your answer? Do you say 1 or 3? Those are the only things that you probably might, So if somebody is asking you how many solutions are there for the system, is it 1 or is it 3? 1. Okay. This is a unique solution. Even if it had, say, 8 variables, okay, it's still a unique solution which is given by this set of numbers. And the reason why it's boring is because there is nothing else going on here. Okay, there is not a lot of information or conceptual stuff that comes out of this example, so that's why it's kind of boring. Okay. It's very unlikely that you will do something like this in this course because there is nothing useful coming out of that. Okay, now let's do the next one. I want you to try the next one yourself. Okay, where is my, yes, I cannot keep this down today. So, all right, the next example, please do this carefully. X1 plus 6x2 minus 3x3 equal to 6, negative 2x1 minus 4x2 minus 3x3 equal to -1, and 3x1 plus 6x2 minus 2x3 equal to 10. All right. Go ahead and see what happens with this. I'm expecting some weird things to happen. Okay. In your opinion, what would be a good first thing to do here? So asking opinions in math, yeah. R3 minus R1. Okay, that's not bad. So something else you could have done before that, but well, you know. Okay. I had something else in mind and not hearing that, but it's okay. You know, is there anything that you could do with the first row immediately? You don't have to do it, but yeah, divide the first row by 3. Okay, because I gifted multiples of 3 everywhere. If this was a 7, I wouldn't do it. You don't have to. If something else is working for you, stick with it. 1/3 R1, because I always like to have a 1 there. Okay, so it's not about liking. You should have 1 there. 1, 2, -1, 2, and then let's just take it slow. Okay, keep the others for now. As long as none of you are doing any legal operations, it's okay. So don't subtract 2 from the first row. Okay. All right, now I could do R2 plus 2R1 and R3 minus 3R1, or if you had some other first step, do what you had. Okay. 1, 2, -1, 2. R2 plus 2R1 would be 0, 0, -5. Three. And R3 minus 3R1 would be 0, 0, -5. And 4. Okay. If you look carefully, you can kind of sense trouble in the last 2 rows. Okay, because here it looks like 0, 0, -5, and a 3. This one looks like 0, 0, -5, and a 4. Okay. Something is not right. Now, if you're not saying that, let's keep going, because this is still not an REF. You can divide the second and third rows by -5. But the seeds of trouble have been sown already. Okay. And this is why example 2 is kind of a standalone case which you should always look out for. Okay, so let me just start from here. -1/5 R2 and -1/5 R3. One, two, -1, 2, 0, 0, 1, -3/5, and 0, 0, 1,
Professor,
4/5.
I think in the last row it's supposed to be 1, not -5.
Where?
In the last row.
Oh, that one? That's even better. That's good. I need to avoid these mistakes. Which one? Let me see. R3 minus 3R1. Oh, yeah. -2 minus 3 times -1 is 1. So this should be a 4. Yeah, people online, if you spot it, if you could unmute and say probably I can catch it earlier because by the time I look here, it's too late. But thank you for the feedbacks. So you can do R3 minus R2, and you get 1, 2, -1, 2, 0, 0, 1, -3/5, and 0, 0, 0, okay, because you're doing R3 minus R2. This would be 4 minus -3/5, that's 4 plus 3/5, which is 23/5. What kind of a story is that last row telling us? If you just read it out in terms of equations, what does it say? Yeah. 0 plus 0 plus 0 equal to 23/5. Now, do you believe it? You shouldn't. Yeah. So what is the meaning of this answer here? No solution. Yeah. It's called an inconsistent system, which I think I mentioned at the beginning of section 4.1 somewhere. Okay, the system is inconsistent, which means that something was wrong when the system was set up in the first place. Okay, that equation had some fundamental mistakes, so that's why we are ending up with the situation. How do we say a system is inconsistent if the REF has 0, 0, 0 and a non-zero entry here? Okay. So a telltale sign of an inconsistent system is the following. You have 0, 0, 0, 0, augment a non-zero number. When you do the REF of a system, if you have a bunch of zeros here, and this is not equal to 0, if this is equal to 0, no harm done, okay, because 0 is equal to 0, okay, that is fine. If this is equal to 1 or some other number like 23/5, okay, then the system is flawed or it's inconsistent. And such a system has no solution. There is no point in going back and trying to solve for anything in this point. Okay. All right, so it's important to understand what an inconsistent system is and what to expect in the REF of that kind of a process. So example 1 had unique solution, example 2 no solution. Okay. Any questions about this? All right, now comes the most important example. Okay.
Wait, professor.
Yeah.
For the when you divide by -5 for row 3, shouldn't it be 0, 0, comma -1/5?
Are we talking about the top board there or the bottom one here?
That one right there.
This one?
Yeah.
Divided by 5 before we switch to 5.
Yeah, it's just like on the left here where you say -1 plus R3.
Mm-hmm.
That was just from the previous when we thought it was.
Oh, I see. Okay, okay. This one shouldn't be here, right? Okay. Yeah, because I made a mistake in the previous one. I think you probably might be referring to that.
Okay. I think I
Yeah,
see
yeah,
it now.
sorry.
right.
Yeah, I forgot to remove this part here. Okay. Everything else consistent? No pun. All right. Example 3. Now pay attention to this one. Okay. This is where all your success of chapter 4 will be based on. Just going to switch some numbers, but comes with a whole baggage of concepts. Okay. So the example 1 was good. Example 2 was important in an inconsistent system kind of way. Okay, this is very important. X1 minus 2x2 plus 3x3 plus 2x4 plus x5 equal to 10. 2x1, yeah, 5 variables, right? 2x1 minus 4x2 plus 8x3 plus 3x4 plus 10x5 equal to 7, and 3x1 minus 6x2 plus 10x3 plus 6x4 plus 5x5 equal to 27. Okay. So the example is very important, not because it has got 5 variables, okay, but for a different reason, which we'll be seeing. What is the first thing you observe here? So that's it. I don't have any more equations to give you. So there are 1, 2, 3, 3 equations and 5 variables. So what is wrong with the system? Ideally, what should we have for a system of linear equations? What is the most ideal situation? We should have the same number of equations and variables. Okay. Examples 1 and 2, whether we have unique solution, no solution, we had 3 equations and 3 variables. Here we have 5 variables, only 3 equations. So let's write the augmented matrix, which can be a little bit lengthy now because there are 5 columns. Remember that the variables are columns, the equations are rows. So we have 1, -2, 3, 2, 1, augment 10, 2, -4, 8, 3, 10, augment 7, and 3, -6, 10, 6, 5, 27. Okay, so it's a 3 by 5 matrix on the coefficient side plus the augmented column. So do your typical row operations. Okay, even if the system is a little bit lopsided, you still start with getting the REF. So R2 minus 2R1 and R3 minus 3R1. So the first row is not changing. 1, -2, 3, 2, 1, 10. Okay. R2 minus 2R1. That's going to be 0, 0, 8 minus 6 is 2. 2 minus 4 is -1. 10 minus 2 is 8. 7 minus 20 is -13. And please correct me if I am making any mistakes. Okay. 3 minus 3 is 0. -6 minus 2 times -6. 2 times -3, that will be 0. 10 minus 9 is 1. 6 minus 6 is 0. And 5 minus 3 is 2. And 27 minus 30 is -3. Now, did I survive that one? Okay. Now, you could swap the 2 rows and then change it, or change it, then swap. It's your choice. Okay, maybe swap and do it. At some point, you have to swap. So, R2 swap R3. To 10, 0, 0, 1, 0, 2. why does this look shorter? Oh. Need to get glasses. 1. So 0, 0, 1, 0, 2, -3, since I'm planning to swap row 2 and row 3. And 0, 0, 2, -1, 8, -13. Did I copy it right? So all these things are the same as what you were doing, okay? And then you can do R3 minus 2 R2. Make sure that you don't lose any ones and zeros you got so far, okay? The whole purpose is to create more zeros and ones, so R3 minus 2 R2. Don't fall into an infinite loop of creating ones and zeros. Okay? Just move forward, don't destroy what you get. 1, -2, 3, 2, 1. 10, 0, 0, 1, 0, 2, -3, 0, 0, 0, R3 minus 2 R2, -1, 4, -7. Almost there. 99% of that is done. Just need to negate the last row. Okay, so -1 R3. Which if you want, you can just write it here instead of copying it all over. Okay, so this followed by -1 R3 will give you 1, -4, and a +7. As long as you know what you're doing, you can merge different things into the same matrix or do it separately. All right, everybody paying attention here? All right. This is where all the concepts kind of creep in. Okay. First thing you should do is try to circle all the leading ones. Those are your pivot ones for each row. Okay. So each equation has a leading one in this particular case, may not be there for all cases. Identify the columns that carry the leading ones. Once again, columns are the ones that go vertically from top to bottom. Okay. So identify the columns that have these leading ones. In this case, column 1, column 3, and column 4 have the leading ones. Remember that the columns correspond to variables, those variables which correspond to these columns. Okay. These are called the pivot columns. Which means they have some importance here. Okay, that's why it's called the pivot columns. The variables corresponding to the pivot columns a lot of writing. Are called the basic variables. And so in this case, x1, x3, and x4 are basic. Okay. So these are not random. These are based on the position of the leading one. That's why these calculations are kind of critical at this point. Okay. You cannot just swap the columns and make things happen. These are religious things for us. Okay. So x1, x3, and x4 are basic variables. So there are two other variables here, x2 and x5, which do not carry the leading ones or the non-pivot columns. Okay. Those are called the free variables. So x2 and x5 are free. Free as in free ice cream. Why is it called free variable? Because this is a system with too many variables and fewer equations, okay, which means that there is a lot more freedom to move around. So free means it's a possibility of an infinitely many number of solutions. Just like if you have one equation and two variables, okay. If I just give you say x plus y equal to 5 and ask you how many solutions are there, infinitely many, because there is 1 degree of freedom, okay, because you're on a straight line, you can go anywhere you want. So in this case, there are 2 degrees of freedom here. Okay. X2 and x5 are free, which means you can take any value. It's a tradition to just give some letters to this. So you will see that your textbook has got some letters S, T, U, V, and so on. Okay. I don't really insist that you should do it, but if you want your answers to match your textbook, it's probably good to follow this practice of giving some letters to free variables. But with or without the letters at this point, you need to now solve for the basic variables in terms of the free variables. For the basic variables in terms of the free variables. This free variable concept is something we are going to take through the next 3 weeks. So please don't forget this. Okay, when we start doing eigenvalues and eigenvectors, we're going to just keep on doing this process. Okay. So now this is where the REF is useful. Go to row 3. So unlike the previous 2 examples, we are not expecting clean numbers because got all these free variables hanging around. Okay. So we have 0x1, 0x2, 0x3, x4, which is a basic variable, minus 4 x5. I just denote x5 by v. So x4 minus 4v equal to 7. So x4 equal to 7 plus 4v. V is free, which means you can take any value. It could be 0, negative, positive. Okay, it's infinitely many solutions here. Go to row 2. Where is my REF? I don't want to lose that. So row 2 gives you x0, x1 plus 0, x2 plus x3, which is a basic variable. Okay. Plus 0x4 plus 2x5, which is 2v equal to negative 3. So x3 equal to negative 3 minus 2v. Now the most complicated row is the one that we did not touch yet. Okay. And this is where the REF versus RREF, the dilemma comes in. Right? If you are doing REF, then you have this whole equation remaining in its raw form. So we have x1 minus 2x2. x2 is free. Okay. x2 is your u up there. So x1 minus 2x2 plus 3x3, which is plus 3 times negative 3 minus 2v plus 2x4. x4 is somewhere here. So plus 2 times 7 plus 4v. That's my x4. And then you have plus x5. x5 is v. Equal to, oh, I erased that one. What was the first? Oh, 10. Okay, thank you. So at this point, the only variable remaining, okay, irrespective of the complicated appearance to this equation, is x1. Okay. So let's just clean up the other terms. This is negative 9. This is a negative 6v. That's a positive 14. and a positive 8v. So we have x1 minus 2u. You have minus 9 plus 14, which is plus 5. Then you have a negative 6v plus 8v, which is plus 2v. And then you have a plus v here. Equal to 10. Assuming that I did not miss anything when I distributed terms. Negative 9 plus 14 is 5. Negative 6v plus 8v is 2 plus 1 is okay. All right, so we can bring this 5 to the right hand side and write x1 equal to 2u minus 3v plus 5. So now things are kind of scattered all over the place, okay? And this is where you have to collect your answers into a single vector, x1, x2, x3, x4, x5. This is something you have to do, whether you replaced your x2 with u or kept it as such. Okay? At the end, you should write your answer in this form. So it's x1 is 2u minus 3v plus 5. Okay, that is your x1. X2 is u. I'm just going to put plus 0v plus 0, just so that I have a term for each of those corresponding entries. Okay. X3 is negative 3 minus 2v. So it's 0u minus 2v minus 3. Okay, just keeping things aligned nicely. X4 is right here, 0 plus 4v plus 7, and x5 is v, which is 0 plus 1v plus 0. So the reason for writing in this format is so that now we can separate it into 3 parts. Okay. So there is a u part, that is the first free variable, u times 2, 1, 0, 0, 0, plus v times negative 3, 0, negative 2, 4, 1, plus a set of numbers which does not have any free variable attached to it. Okay. 5, 0, negative 3, 7, 0. This is the final answer. So x equal to x1, x2, x3, x4, x5. This is what you call as a vector form of the solution, because you're writing the solution just not in this form, okay, but in a form where you could easily see the free variables and also the components. This is called the vector form of the solution. So the question usually says that, solve the system and write the answer in the vector form, which means you have to just separate out the free variables. Okay. But if you just prefer writing this as x2 and x5, I don't have a problem with it. I don't think it's a big deal that you replace those with some letters, but if you don't want to do it, that's fine. So that should not be the bothering factor here. The concepts were the one I wrote earlier in terms of the pivot columns, basic variables, non-pivot columns, free variables. Okay, that's the take-home concept from today's lecture. Okay. Pivot columns correspond to the basic variables, non-pivot columns correspond to the free variables, and at the end of it, you solve basic in terms of free. And whenever there is a free variable, that just means the system has infinitely many solutions. Okay. So tomorrow we'll do a homogeneous system where the right hand side is 0, but the concept is still the same. Okay. And also look at a couple of conceptual questions and also look at how to find the inverse of a square matrix. All right, so please start doing the homework in 4.2 and 4.3. Okay, these things might look easy when somebody else does it, but when you start doing it yourself, you will get into all kinds of trouble. So just practice, practice, practice. All right, that'll be it for today. I think that's a good place to stop. And I can stay back if you have any questions.
Thank you.